We've already seen that matrix vector multiplication can be visualized as a vector being transformed in one or both of the following ways. So when we multiply a matrix times a vector, we sometimes get a rotation, and sometimes we only get a rotation, and sometimes when we multiply the vector by the matrix, we get a stretch or we get a compression of the vector. And it's possible that both things happen. For example, if I take a vector and it gets rotated, it can get rotated and potentially scaled, maybe doubled in length. And let's take a look at one such example to remind ourselves of this. First of all, here we have the vector 2, 1, which we could visualize as the vector extending from the origin to the location 2, 1. So there's the vector 2, 1, and that is prior to multiplication by this matrix A. So let's go ahead and conduct this multiplication AX. And as always, the second vector's components serve as the scalar multipliers for the columns of the first matrix. So 2 is going to scale the first column, and 1 is going to scale the second column, and by definition we're going to add those results together. So 2 times 1, 0, plus 1 times 1, 2. Well, that's going to give me 2 plus 1 is 3. So the new x component is going to be 3 of this transformed vector, and the y component will be 2 times 0 plus 1 times 2. And that gives us the vector 3, 2. So let's go ahead and plot that vector on the same pair of axes. And what will this vector look like? Well, it's going to be the vector that's 3 units over, 2 units up. And there is that vector. So this red vector is a representation of what we get when we transform x through multiplication via A. And so you can see that two things took place. First of all, there's a slight rotation. We can see that slight rotation between our vectors. So there it is. There's our rotation. And we can also see that this vector has been stretched. We can look at the magnitude of x and see that it will be the square root of 2 squared plus 1 squared, Pythagorean theorem, so the square root of 5. And the magnitude of ax will be the magnitude of 3, 2, which is the square root of 3 squared plus 2 squared. That will give us 9 plus 4, which is 13. So we can see that ax is a bit longer. And we could also compute the angles if we so desired. So we have a stretch and we have a rotation taking place. So we can see this is a transformation. Now, when we multiply x by a, we always get rotations and stretches or compressions, but there are specific features that some transformations have that make them what we call a linear transformation. So not all transformations are linear, but a transformation is called a linear transformation. Now we write it like this. We give the transformation a name, and its name is t, or at least in this case, we're calling it t, just stands for transformation. And this notation here suggests that this is the input. So we have a vector that is in Rn. Okay, so this could be in the two-dimensional case, it could be in R2. And the output is another vector, and that's going to be in Rm. So what this implies is that we're going from n dimensions to m dimensions. Now in some case n and m could be equal, meaning we could transform a two-dimensional vector into another two-dimensional vector, and maybe that's all we would think that would be possible. But it's actually possible to take a two-dimensional vector and transform it into 3 dimensions, or take a 3-dimensional vector and transform it into 2 dimensions. Now, if you think about this, we do this all the time in graphics, video games, videos, where we have shadows that could be 2-dimensional projections of a 3-dimensional object. So it's natural to actually project across dimensions. Now, the 2 properties that must be obeyed for the transformation to be called linear are these 2 right here, where c is a scalar and x and y are vectors in Rn. So those are our inputs. Okay, so here's what's going to happen. The transformation of a vector that gets scaled is the same thing as transforming the vector first and then scaling it. So I want to give a visual representation of this. So this is suggesting that if I have some vector, let's just draw it over here and we'll call this vector x. If I were to scale it, multiply it by c, some scalar, and we'll just, for illustrative purposes, suppose that's going to stretch it. If we were to do that, and we were to then transform it, so maybe our transformation will rotate it and maybe it'll compress it just a little bit. So let's just illustratively say that this is the transformation of that scaled vector. Okay, so here is x, this longer vector I've just drawn as c times x, and then the transformation will rotate and scale the cx vector, and it will make it into this new vector here. Now, a linear transformation will have the property that if you scale it first and then transform it, that you should get the same answer as if you rotated it first and then scaled it. That is, you transformed it first and then scaled it. So visually what that would mean is that, let's just say we took this vector x and we transformed it. And maybe what would happen is that rotation takes place and that transformation also scales that vector. And you can see that right now, visually, t of cx, the transformation of the scaled vector, is not the same thing as the transformation of x. But now if you scaled it by a factor of c, what that would do is it would stretch it, compress it back down, and it should give us c times t of x. So notice that the idea here would be that whether you scale it first and then transform it, or you transform the vector first and then scale it, you get the exact same result. So I'm gonna point this out here, that this is the exact same result. And I'll put that in words. I'll just say scaling and then transforming equals the same vector, I'll write it like this, transforming and then scaling. So notice that it shouldn't matter in which order you do these things. For this transformation to be called linear, it must produce the same result either way. Now let's look at property 2. Property 2 has a very similar idea here. It says that if you add together 2 vectors and then transform it, you should get the same thing as if you transform the vectors first and then add them. Okay, so visually, we would maybe have 2 vectors, x and y. And maybe I'll just draw them like this. Okay, so you have 2 vectors, x and y. You add them together. Okay, so what does that mean to add them together? Well, that means you put them together tip to tail. Okay, so let me take that away and put it on the tip of x like that. So there's y, and this represents x plus y. And so here we get, when we add together two vectors, we get some resultant vector, which we call x plus y. Now if you take that new vector that you form and you transform it, just to avoid some visual clutter, let's just say that what happens is it maybe really scales it and rotates it into the third quadrant. So we'll refer to this as the transformation of that resultant vector that we get when we add together x and y. Now if this is a linear transformation, not all transformations are, but if this is a linear transformation, we should get the same result when we transform x, we transform y, and then we add them together. So here's x again. Let's just say that when we transform x, we get a vector that maybe points up here. Okay, so there's the transformation of x. And when we transform y, maybe the vector that we get points down like this. Okay, so that's just the transformation of y by itself. Now, once again, when you add two vectors, here, the transformation of x with the transformation of y, notice that if I actually attach this vector to the tip of the transformation of x, that I indeed arrive at the exact same location as if I added them first and then transformed that sum. So let me just go ahead and erase this here. Whoops, not all of it, just that stuff. Okay, well, we get the idea. So if these two properties hold, we have what's called a linear transformation. And if you kind of think back to linear functions have nice properties. Essentially, this kind of means, but not really, this kind of looks like you could almost factor out the c, right? You could almost factor out the constant. This is not multiplication, so we can't really call it factoring, but you can kind of pull that constant out if you have a linear transformation. And that could be convenient. Also, the transformation operator is linear in that it kind of distributes to x and to y. Okay, so you can sort of factor out a constant, and you can also distribute the transformation operator. I don't want to write that down because it's not, again, t of is not t times, but I just want you to be able to visualize it as something that you've seen in the past. So I want to write also that transforming the sum of x and y equals transforming x and transforming y and then adding them together. At this point, this is just a definition. I'm not telling you why this is useful quite yet, because we're going to just become familiar with how do we test for a linear transformation. Okay, let's take a look at one. Let t be the transformation, so you can kind of think you can think about this as a function being applied to vectors. And let's say the transformation scales the x component by 2 and the y component by 3. So in other words, if I input a vector into this function, what it's going to produce, you can see that this is the input into the function, and this is the output. So think about this as very, very identical to me giving you a function like this in algebra, 3x plus 2. Okay, so you know exactly what to do if I gave you a value of x here. If I said calculate f of 2, well, what would you do? You would take 3 times 2 plus 2. 6 plus 2 is 8. And so this was your input into that function, and this is your output. The only difference here is that our function is usually denoted by a capital letter, in this case capital T to stand for transformation. It doesn't have to be capital T. And then something happens to that input and it gets output as the components 2x and 3x. So you might have also seen this in algebra where you feed this function an input, and there's sort of like this black box or like a conveyor belt analogy, and this calculates the function of x, and then it produces an output. So if I give this conveyor belt an input of 2, according to our example here, it's going to calculate f of 2, and it's going to give me the output 8. Now in a very similar sense, our vector function, we're going to input a vector with 2 components. That conveyor belt is going to take in that vector, it's going to double the x component, double the y component, and then it's going to output the vector 2x, 3y. Okay, let's take a look at y. Oh, and just as a quick example, let's just say I took the transformation of the vector 1, 1. Well, it's going to double the x component. 2 times 1 is 2. It's going to double the y component. 2 times 1 is 3. And that's going to be my output. So the vector 1, 1 gets transformed into the new vector 2, 3, which again, is just a stretch and a rotation. All right, why is this a linear transformation? So I have to show that when I scale the vector first and then transform it, I get the same result as if I transform the vector first and then scale it by a constant. So basically we're just going to show that the left-hand side equals the right-hand side. And here's how we can do this. So the left-hand side, let's take a vector, generically calling its components x and little y. Notice that I don't have vector hats over here, so this little x and this vector x are only related in the sense that this little x is a component of the vector x. Okay, so what's going to happen here? Well, first of all, this says scale first, right? So if I scale the components first, that input vector becomes cx, cy. Next, I want to transform it. So what does the transformation do? Well, it doubles the x component. So the x component is cx, and if I double that, I get 2cx. The y component is cy, and if I triple that, I get 3cy. And that's my output on the left-hand side. So it's 2 times c times x, and the y component is 3 times c times y. I'll put those multiplication signs in there just to emphasize that these are all multiplied together. Now let me show that that's the same thing I get if I take the transformation of x first. There's a generic vector that I'm giving it. And now if I transform that vector, c times the transformation of xy, well, it's going to double x, it's going to triple the y, and now if I scale it, well, notice that if you multiply 3 numbers together, you always get the same answer, right? It doesn't matter what order we multiply numbers by. So c times 2x, 2 times x is the same thing as 2 times c times x, and c times 3y is 3 times c times y. And you can see that those are, in fact, equal to each other. In fact, they're identical, and that's just what we're trying to show, that we get the same answer. Now let's do property 2. So in property 2, we need to show that if we add together 2 vectors first and then transform them according to this transformation here, we get the same answer as if we transform them first and then add them together. Okay, so again, show that the left-hand side equals the right-hand side. Okay, so let's call x, we have to kind of distinguish the components of these 2 vectors. So let me call this x1, y1, and maybe I'll just refer to the components of y as x2, y2. That way they're similar but not the same. Okay, well when I add together 2 vectors, which is what I have to do first here, I add their components. So x1 plus x2. And here, if I add the y components, it's going to be y1 plus y2. Now that's a vector. Remember, x1 plus x2 is just a single number. We just don't know what they are, so we can't actually write it as a single number. But that's a single number right there. And this is a single number right here. And now, what do we need to do? Well, now we need to transform that vector, and the transformation says double the top, triple the bottom. Okay, so this will mean that if I double the top, I'll get 2 times x1 plus x2. And if I triple the bottom, 3 times y1 plus y2. Now, sure, we can distribute that if we choose. We can leave it like that for now. Okay, this is still 2 times, 3 times. Now let me operate on the right-hand side. So the right-hand side says, take the transformation of x, take the transformation of y, x2, y2, and then add them together. So if I transform x1, y1, I'm going to double the top, triple the bottom. So 2x1, 3y1. Now if I triple the top, double the bottom of the second vector, I get 2x2 and 3y2. And now I add them together. Well, if I add them together, I get 2x1 plus 2x2 and 3y1 plus 3y2. And what I want to check for is is the left-hand side the same thing as the right-hand side? Kind of, not quite. So just to make that totally obvious, I could factor out a 2 here, or I could distribute the 2 over here. And you can see pretty quickly that if I factor out the 2 here, I'll just do it as a factor instead of a distribute on the left. And if I factor out a 3 on the bottom, you can see that, once again, these are equal, and I've proven that property 1 and property 2 both hold. And so this is a linear transformation. Why? Well, because it obeys both of the laws of what a linear transformation requires. Let's look at another example. In this first example, notice that we took a vector. The input was in 2 dimensions, R2, and the output was in R2. So this transformation, let me just make a little box here. This transformation took a vector, started in R2, and created another vector in R2. In the second example, notice that our input is a 2-dimensional vector, but our output is a 3-dimensional vector. How can we possibly get that? Well, all we have to do is somehow get a third component in there, and the way we'll do that is we'll leave the first components the same, so it doesn't really transform the top components, but it adds a third component that's going to be the sum of x and y. Okay, this is just one example of such a transformation. So this one takes a vector in R2 and creates a 3-dimensional vector out of it. So show that this one is a linear transformation. So property 1, we're going to show that if I transform c times this vector x, y, I don't have to use x1, y1 here just because it's only one vector for the first property. I need to show that that is the same thing as transforming the vector first and then scaling it. Okay, so once again, we're going to show that the left-hand side is the right-hand side. So if I scale this vector by c, I get cx, cy. No difference there. A very similar process across showing anything as a linear transformation. Now, what do I do to transform it? Well, the transformation says keep the first 2 components the same as the original 2 components. Okay, well, the original 2 components are cx and cy in this input vector. And the bottom component is going to be the sum of the components that we're transforming. In this case, cx plus cy, because that's our input. Now, not much more I can do there, but I'll go ahead and transform xy first. So if I transform xy, it says leave the 2 top components the same, and then whatever the input is, sum the 2 components and put them down on the bottom. Now, multiply by c, and so if I multiply a vector by a constant, it's going to scale x, C will scale y, and C will scale x plus y. Well, you can see that these are going to be the same because now I can distribute. These are just real numbers in these vectors. And I get cx plus cy, and the whole goal was to show that the quantity on the left is equal to the quantity on the right. Now, also, again, this is not sufficient. We need to show that the second property holds as well. So if I transform the sum of two vectors, in other words, if I add them first and then transform them, I should get the same answer as if I transform the first, transform the second, and then add them together. So let's see if that happens. So first sum, this will give me the transformation of x1 plus x2, y1 plus y2. And now if I transform that, let's just follow the rules of the transformation here carefully. Leave the top components the same as the original top components, y1 plus y2. And then the third component will be the sum of the two components that we have. So the sum of x1 plus x2 plus y1 plus y2. I'm not putting parentheses in there because it's just addition. And I want to show that that gives me the same answer as if I transform them first and then add them. So transforming x1, y1. Okay, so leave the two top components the same. The third component is the sum of those two components. Here, same idea. Leave the top components the same as the original two components. Third component is the sum of those two components. Now add them together. So adding together x1 and x2. Adding y1 and y2, and adding together x1 plus y1 plus x2 plus y2. Now, they do appear in a different order in the bottom component, but there's an x1 there, there's an x1 there, there's an x2 there, there's an x2 there, there's a y1 here, a y1 here, a y2 here, a y2 here. Now, remember, these are just scalars being added together, constants being added together, so they produce the exact same result. We can see that they are indeed equal, and we can see that this is a linear transformation. We'll wrap up with one example that is not a linear transformation, because it might seem that we just go through these same steps over and over again and we always get the same answer. Yes, it's a linear transformation. Not always. Notice the difference here. This input vector, or this function, takes a two-dimensional vector, produces another two-dimensional vector. So it is a transformation, but it's just not a linear transformation. So notice what happens to the input. The two components get multiplied together. That becomes our new top output. And the bottom component stays the same. Let's show that if we take a vector, scale it first and then transform it, that do we get, and in some cases one of the properties might work fine, but the other one may not. Okay, they both have to work. So if I scale first, well, we already know what we're going to get there. It's going to be cx, cy, and the setup is identical, but now what this says is that the output of the transformation will multiply the bottom and top component together, so cx times cy, and the bottom component will remain the same as the input, cy. Do we get the same answer if we transform first and then scale? Let's find out. If we transform xy, well, the top component is going to be the product of the two components. The bottom component will be the same as the original bottom component. And now when we scale, we get cxy on top and cy on the bottom. Now notice that here we have c times c, which is c squared. So this is actually c squared xy and cy. And you can see that these two are not equal to each other. So this property fails. And let's also see that the second property whether it will fail as well. Not always, but sometimes it does, and a lot of times it does. Okay, so if we add first and then transform, do we get the same answer as if we transform first, transform first, and then add together? So if we add together first, we already know we're going to get x1 plus x2 and y1 plus y2. And if we now transform this, the transformation says multiply the two components of your input together, x1 plus x2 times y1 plus y2. And then the bottom component will be the same as the original bottom component of your input. Now I'm going to just do a little bit of foiling here, just to get this a little bit further. If I distribute, I'll have x1 times y1 plus x1 times y2 plus x2 times y1 plus x2 times y2, and in the bottom I'll have y1 plus y2. So what do I get on the right-hand side? Well, if I transform the vector, it's going to multiply the components together, leave the same original input component for the bottom. Here, same idea, x2 times y2 and y2 on the bottom. And now if I add those together, x1 y1 plus x2 y2, and in the bottom component I'll have y1 plus y2. And you can see that here we have the same first term. We have an x2 y2, which is also part of our second vector, but the right-hand side is missing. These guys are missing, right, in that other vector, so these two vectors aren't equal. Even though their y components are the same, the x components are not. And so this also fails. Not just one, but fails both properties. And it has to have both properties to be a linear transformation. So this is not a linear transformation. Now, why is this all useful? Well, it turns out that if a transformation is linear, then the transformation has some convenient and useful properties we're going to come to appreciate in a forthcoming lesson.